Okay, finally, the good old VGA is working now. So I want to talk about security by obscurity. And before we start talking about this strange title of the talk, I would like to introduce myself. So I'm Sebastian Schrittwieser, and I'm a professor for information security at the St. Pölten University of Applied Sciences. So I would like to welcome our previous speaker to our university and introduce our curriculum to him, because I think we are hitting this sweet spot between security and development very good. So I think our students come out of the university and know how to develop secure applications. And I'm also the head of a research center on security, where we're focusing on targeted attacks on corporate infrastructures. So let's talk about the title, Security by Obscurity. What's that, and why is this the title of my talk? Because it's not something very good. So the definition is, security by obscurity is the reliance on the secrecy of the design or implementation as the main methods of providing security for a system. And yeah, this term is a few hundred years old, and it was used in the military. And we know it from a security perspective. We know it in cryptography. So the basic idea of security by obscurity is that a cryptographic algorithm is only good and secure as long as its implementation and its details are not known. And that's obviously something that is not a good option for a cryptographic algorithm. So all the algorithms we have nowadays are open, and they're secure, even though everyone can look into the algorithm and knows how it works. And what we see in security is that this security by obscurity principle is often used in different areas, and one of them is web applications, and web applications in combination with mobile apps. That's one part of our research, that we analyze the security of smartphone applications. And yeah, I would like to show you some examples where this security by obscurity was used on a protocol layer, communication between the smartphone application, the client, and the server, and how it failed and what you can do against it. So when we look at web applications, they are quite transparent to the end user. So you can see quite a lot from the client by just looking at the web browser or looking a little bit inside. So you see the URL bar, you see all the link targets before actually clicking them, and you have the web inspector. So web application on the client side is very transparent. So everything is visible to the end user, and it's quite obvious how the application, at least on the client part, works, and how the communication to the server works. And hiding the communication protocol between the server and the client is not something that is feasible, because everyone can look inside, and it's quite obvious how the system works. And if there are things in the communication that are not secure, then it's quite easy to reveal them. So for example, in the OWASP top 10 from so the previous iteration from 2013 had this insecure direct object references. So one example of this would be that you have some system where you can display some invoices, and if the invoice ID, for example, is guessable because it's just counting up, then it's quite obvious how to display other invoices in the system by just modifying this parameter. So when you look at the traditional web applications and the communication, you see that on the client there's little program logic. So of course, sometimes, for example, in a game, there might be some logic on the client, but most of the calculations are done in the web application on the server, and the data is more or less delivered as instant meal and is just presented through the web application than client side. When we now look at smartphones and smartphone applications, we can see a trend that more and more of these operations are moving to the client, to the smartphone, and yeah, more complex operations are done there. Often, even the raw data is delivered to the smartphone, and then all the data modifications and things are done on the smartphone before presenting it to the end user. So there is a lot of program logic, and there's the presentation layer. And there was a new OWASP Top 10 that was introduced last year, and there was a release candidate 1 that had this underprotected APIs part of the OWASP Top 10. This was the 10th bullet point in this list. Unfortunately, it was removed in the final version together with almost half of the OWASP Top 10 and replaced by something else. But that's a different story. I think it's a pity that it was removed, because that's something we see every day and everywhere, that we have these very powerful APIs to a web application that are able to deliver quite some data to smartphone applications. And by looking at them first, we as security analysts often find the first vulnerabilities by just looking at how these communications protocols work. And I would like to show you a few of the findings we and other research groups found in the last few years of well-known apps and not so well-known ones. And all of these vulnerabilities that I show you don't exist anymore, so there were responsible disclosure processes before this presentation now. And so that you get an understanding on what typically goes wrong when we just look at the applications from a transport layer perspective, so from the communications protocol. So let's start with the first app, with Tinder. They had the problem with the locations of the profiles. So the Tinder app shows you the distance to the owner of a profile you're watching. And in earlier versions of the API, it was done by just sending the latitude and the longitude, so the GPS coordinates of the profile you were accessing, to the smartphone. And then it was something like this, that really the latitude and the longitude were inside. Of course, this was not displayed in the application itself, but it was just compared to the location of the smartphone that was looking at the profile, and the distance was calculated. And in the smartphone app, it was just shown this profile is 7-something kilometers away. But providing the exact location is obviously not a good thing, and security researchers were able to extract this and just putting the profiles on a map. Then the vulnerability was fixed by just replacing the latitude and the longitude parameters by a distance value. So it was this distance in miles, and that was 5.85 something. So the distance in miles with 15 digits after the comma. That's of course very accurate, and maybe it doesn't make sense to have it in this accuracy, because in the app it shows something like 5.8 kilometers. What could you do then to pinpoint the exact location of a user on a map? You can triangulate, of course. You just have one location and a distance, then you go somewhere else and have another distance, and then you just fake the GPS location on your phone or on the transport, do it a third time, and you see this location is exactly here in this room. Another example, SuperSwap. That's one application in. So there are several of them, and they are really strange. So this is something you take a picture, and someone else takes a picture, and you swap the pictures, but you don't know with whom you you swap the pictures. So it's just randomly chosen, and they say they do it with someone else that takes a picture at the exact same moment. Let's have a look at one of these apps. It was not SuperSwap, but it was another one. They had their pictures stored on their web server, and this was the structure. If you look at the file name, of course, you need 3 lines of code, maybe a huge hard drive and one night, and you can download all the pictures that were stored in this application. Of course, they were never deleted from the app, so the idea was you swap the pictures and then nobody else will see your picture never again, and of course they were still stored on the server, and you were able to download, you would have been able to download all of them. That's another app in this area. Now the file names look a little bit better, but still you can see a little bit of structure in the file names. At least they're not guessable anymore. But what you can see at the beginning, there's IP and WP. It's iPhone, Windows Phone, and for Android they don't have any prefix. Then we have some hardware ID. So that's, for example, the UDID on the iPhones and so on. And then the end, we have a timestamp. It was interesting to see this timestamp because the app developers said you will get a picture of someone who took this picture at the exact same moment, but sometimes the timestamps were 2 years old. So it's obviously that they just take one random picture out of their pool of pictures they have, and they just send it to you. And in Android, for example, the hardware ID was the EMI. That's also something you don't want to have your pictures stored on this web server. Another problem here was that there should be some atomic operation. So you take a picture and you send it to the server, and for sending a picture, you also receive one. It shouldn't be that you don't send a picture, but you receive one, because then you would be able to download everything. But exactly this was implemented like this in this web application. So there were 2 requests. The one was, hey, I have a picture for you, upload it, and then the app there's another request that says, please give me a picture. And they didn't check server-side if you uploaded a picture before downloading one. So we were able to just send this, hey, please send me a picture requests all the time, and it will send you thousands of pictures, and they don't care. We were able to run this all night and download all the pictures. Interesting with this file structure is you exactly know when the picture was taken, and if someone took more than one picture, and we had this, then you were able to make some kind of stop motion movies from all the pictures of one user of the application. A similar problem exists in Snapchat. So if you look at the requests of Snapchat, then you can see there is this updates request. That's something like when you start the application, it says, hey, is there something new for me? Is there a new picture for me? And if yes, then it gets downloaded. That's this blob. So the picture is encrypted. The key is not very well protected in the binary, but that's another story. And then it gets decrypted on the phone and can be displayed. After the countdown is over and the picture should be deleted, then there is another request sent to the server that says update snaps, which marks the picture as deleted on the server. Of course, we don't know if the pictures actually get deleted on the server, but at least it's not possible to download them anymore, so sending another updates request won't give me the picture again. But you don't have to send these update snaps. You can just use the updates to download the pictures, but then you don't have to delete them. And there were lots of apps and web applications did exactly this. For example, Snap Save. They just downloaded the pictures by rebuilding the client, and then just download them and didn't delete them. And then something like this, of course, had to happen. Snappening, thousands of photos were released to the internet. of course, this was not a problem of the Snapchat server. All of these pictures came from some third-party application that downloaded the pictures through the API, and then yeah, they had some vulnerabilities on their web server, and all the pictures were downloaded. Another example, WhatsApp. That was the first app we analyzed, and all these messengers were quite interesting at the beginning, and these vulnerabilities are from around 2012, 13. Obviously, they are fixed now, but this is how the protocol looked like for Snapchat a few years ago, when Snapchat had already several million users worldwide. So when you launch WhatsApp for the first time, it will ask you for your phone number, and then they send you some SMS with some PIN code, and you have to type in the PIN code, and then you're authenticated. And that's the request the phone sends to the server when you type in your phone number and press next. They send the phone number, obviously, to the server. They send it twice. One time without the area, the country code, and then the country code again. They send the UDID, and they send an authentication code, this 7116. And that's exactly the authentication code that was then sent via SMS back to the client. So in this case, from protocol side, this authentication code was created on the client, was sent to the server. The server created an SMS, sent it back to the client, and the client then checked itself if it's authenticated or not. Of course, you were able to get the code out of the app or from transport, and then just authenticate via any number. Just type in any number, get the code, and you're authenticated in WhatsApp. They even didn't check if this is a three digits number. You were able to send them anything. They process it somewhere on their servers and then send an SMS. So you were able to send free SMS worldwide to any number. It only said WhatsApp code, and then there was the code, but still you had around 120 characters left. Another interesting problem, status messages. You just changed your status message, pressed OK, and something like this happened. Just 3 parameters, so the country code plus your phone number, and the new status. So this actually looked like this for changing the status code of anyone by just typing in the phone number. So you only have to know the phone number of someone. Obviously, again, a bad idea. They fixed it by, so there was a website, whatsappstatus.net, with 2 input fields, phone number and status, and you were able to change the status of anyone. And then this was fixed a day later, and then the researchers found out that it was fixed by just blocking the IP address of this service. Then they said, that's not a good fix, obviously, and provided some Windows application where you're able to send this request from your own computer. Then they fixed it by checking if from the same IP address someone is logged into the WhatsApp account, and if yes, then this IP address was allowed to change the status message. In newer versions, they altogether removed it from this entire functionality and put it somewhere else. Another problem, sending your phone book for number synchronization to the server. This looks like this. All the numbers are sent, and then you get all the numbers back with the status message that have WhatsApp. And of course, they don't check how big your phone book is. So you can send, for example, an entire number range with 10 million phone numbers to the server, and then you get all the status messages. Like this, status messages from the US, hundreds of thousands of status messages that sometimes are quite interesting. Yeah, so what are the countermeasures? What can you do? Sometimes Developers just say, well, the traffic of my web application is encrypted. Nobody can look inside anyway, so what's the problem? Nobody will reverse engineer the app, and we have transport layer encryption. But that's, of course, not a good countermeasure, because it's encrypted on the transport, but you need secure endpoints. And what you can do is you can do an interception, a man-in-the-middle attack, where you're in the middle and you make two encrypted connections out of one. And both of them are encrypted, and both sides think they're connecting to the correct endpoint. If there wouldn't be certificates, of course, but in this case, certificates don't help you much, because work like this. So you have the secure connection, and there is some trusted third party that issues a certificate to some service. The certificate is then sent to the client. And the client has a trust relationship to the third party and says, well, that's okay. So you can prevent an attacker that is sitting somewhere on the net to do like, or to impersonate this web service. But the goal here is just to ensure that the client communicates with the right server. But in our case, when we analyze applications, the attacker doesn't sit on the internet somewhere, but he sits on the phone. So the attacker can control his own phone, its own endpoint, and then just adds a CA to the phone, his own phone, say everything that comes from there is okay. And the second goal would be to ensure that the client does not connect to the wrong server on purpose. And that's not something you can prevent with just transport layer encryption. Another solution might be my app checks if a particular certificate is used, so using certificate pinning. That's obviously a good idea to have it. It increases the security because only one particular certificate is valid and not one from any trusted third party. It even reduces your costs. You don't have to get new certificates every now and then. Less flexibility is a downside, because if you want to change the certificate, you have to update your clients, and your users have to update the clients. But again, it doesn't work against this type of analysis, because there are applications that you can install on your attacker phone to disable this certificate pinning system-wide. So for example, for iOS, there's this SSL kill switch, and for Android, for example, Just Trust Me, that you can install, and it prevents certificate pinning on a global operating system layer. So certificate pinning also relies on a trusted client, which does not exist. So what can then be a countermeasure? Actually, it's quite easy. Never ever trust the client, even if it's your own client, because it's in an environment that you can't control. I know this advice is many, many years old, but still, this is a problem, and we see this every day, that the clients are trusted, and this type of vulnerabilities exist in this by manipulating the transport layer. So we look at all the applications we had. What did go wrong? So in Tinder, don't send data that the app doesn't show anyway. The GPS coordinates were sent. You don't need them in the app. Don't send data needlessly precise, so with this 15 digits after the comma. For the super swap, don't make the URLs guessable. We were just counting up the pictures, and they revealed information through the URL, like the timestamps and the IDs of the phones and everything. For Snapchat, the problem was that there was a control flow logic attack, so we were able to get more out of the app by using another control flow in this case, but just omitting one of the requests that were sent. And for WhatsApp, don't perform security critical operations on the client, of course. So this security code was created on the client, and it was checked afterwards on the client. perform user authentication before executing operations. So the status message was changed without authenticating the user. And rate limit your APIs. So it doesn't make sense that I'm able to upload 10 million phone numbers as my phone book, and the server just sends everything back as if this would be a normal behavior. So thank you for your attention.
Sebastian, if I look into the faces of the guys here, the most important question is Tinder secure now?
At least this location thing is better now, yeah.
All right, all right. So what's the best practice for storing and protecting the secrets in apps? What to do?
You can't really protect secrets in apps, so that's my other research area I'm focusing on. You can try to obfuscate your secrets in the apps, but better not rely on them and on the secrecy on the client, because you won't have a secure client.
There are always the security researchers. They will find your obscurity.
Yeah.
That's not a solution. And the next question, where can we find more examples on those things? I know you've got a bunch of them, and almost endless. Where's more? Is there a community out there sharing it?
Yeah, there's some sort of community for smartphone messengers. So smartphone messengers are evaluated all the time. We do this every year as a bachelor thesis. Just check what new vulnerabilities exist in smartphone messenger apps. And yeah, all the publications are freely available. So if you're interested, just Google me and you will find them.
So search for your profile and get in touch. It's always talking and communicating. That's very, very important. Maybe one last question. SMIME and PGP vulnerabilities, just found recently. They're again in the press. Are they really important?
The vulnerabilities? Yeah, the vulnerabilities are not in the security protocol itself, but again in the clients. So the clients that implement this PGP protocol were insecure. And of course, this can be fixed on the client, but from my perspective, all this PGP, at least for email encryption, failed, and I would move on to messenger applications that are more modern way of encrypting communication. There are so many things you can do wrong with PGP encryption that it's not something that I see will actually secure communication for the masses.
Fantastic. So the next question, I can only cite it. It's not actually a question. It's a great talk. Thank you for that.
Thank you.
It's a huge pleasure.